Okay, hi everyone. So just a first announcement, you can find the slides at this link. It should be at the bottom corner of every slide. So if you're interested in reading the slides, please go and have a look at that. So the first thing you should know about me is that I'm a software engineer. I self-identify as a software engineer. I've been doing software for as long as I can remember. And it really, informs how I think about things. I'm also an open source developer. I've been doing it since I think about 1994 was the first piece of open source thing I did. And so I've been doing open source for a really long time. And I've also been an employee of Google for about 14 years now. And one of the things that I learned from working at Google is that it runs on computers. They pioneered all of this warehouse scale computing, and they use a huge number of computers. People always underestimate how many computers are in use at Google. The thing is, for most of my life, there's been this great thing called Moore's Law, which meant that if you just waited a couple of years, all of a sudden, all your software got faster. That's started to slow down and started to be less successful. Although if you go and talk to Intel and TSMC, maybe they would disagree with me. But one thing that hasn't changed is that the demand for compute continues to grow pretty much exponentially. And to keep up with this demand with Moore's Law slowing, Google has had to look for alternative solutions. And one of the solutions that we've been very successful with in the machine learning space is the TPU. And the TPU is an accelerator that dramatically speeds up machine learning. The problem, though, we discovered when doing things like the TPU, and this is well known in the IC creation industry, is that as you go to more advanced nodes, the cost of creating the design and the verification increases substantially, and the cost is continuing to go up. As well, the difference between what you should get in theory from a new process technology and what people are actually able to achieve with that process technology is increasingly having a gap. And as I said, I'm an open source developer. And so I thought, well, could there be something to having open source silicon? And so when you think about creating ASICs, I like to think there are three major parts. There's the IP libraries, and there's actually quite a strong history of open source IP libraries. The FOSSI Foundation, which was mentioned, has been around for a long time. It was very involved in the open RISC thing. There's been open cores. And recently, there's been massive explosion in open source IP and RTL based around the RISC-V ecosystem. So we've got quite a lot of open source IP. There's actually also a long history of open source EDA tools. One of the EDA tools that you may have used in the programs that I run is a tool called Magic that's currently maintained by Tim Edwards. That tool is older than I am. And it's actually so old, when I went to go and look at what license it was under, I discovered that it predates the standard BSD license. So it definitely has a BSD license these days, but there's a strong, long history of open source EDA tools. But the last thing you need is PDKs. And when I started this, I couldn't find open source manufacturable PDKs. And this surprised me because, it's been a very long time for many of these process technologies, and I would have expected somebody to have developed this. And when I looked around about, what is a PDK, because again, I'm a software developer, it contained all the low-level information about what you need to make a chip. And this seems to me like the type of thing you need to get anything useful at all. And so I had to search for things like what was out there. And there were some manufacturable PDKs, but they're on very, very old process nodes. And there was a bunch of other stuff that was under restrictive licenses. Although since I've started in this area, we've definitely seen a slow change in things actually becoming open source now. The reason this is problematic, though, is if you look at the fabless Rovana chip, they had fully open source RTL, they used fully open source tools, but they used an XFAB 180 nanometer PDK, and the XFAB 180 nanometer PDK is not an open source PDK. And so if you think about it, this PDK data, because it's so fundamental to the manufacturing, infects the rest of the design and makes it pretty much impossible for them to release something that other people can reuse without having to think. And this hole was a really big roadblock I identified. And so I came up with a plan to solve this, and a plan that I thought was going to change how we do IC design and potentially solve some of those issues that I was talking about with Moore's law ending. The plan had three parts. The first part was we release an open source PDK, we fund some EDA tooling integration, and then we have a SiliconRealization program. So the first part was, release a PDK, do EDA tooling integration, and run a shuttle program to get people into the community. And one of the key metrics I was looking for was number of users. How could we dramatically increase the number of people using tooling, the number of people writing IPRTL, and the number of people using the PDK? And something that I discovered is that in the US, some estimates put us around 70,000 hardware engineers growing at, 6%-ish, which is a pretty good growth rate. But there are 800,000 software engineers, and that's growing at 30%. And that is a much bigger pool of people and a much larger growth rate. And so the other thing that I really wanted to focus on is how do we make software engineers into hardware engineers? So that was the plan, the hypothesis I had. So how's it going? Well, part one was getting this PDK or a PDK that was manufacturable released. And experts in the industry told me this would never happen. You would never be able to succeed at doing this. And then in June 2020, I surprised everyone with this open source PDK. I did the first talk about it at the FOSSI Foundation, and this is a fully open source PDK. It's available on GitHub. You can go to this URL and you can use it for manufacturing. It's under a real open source license. It's under Apache 2 license, and you don't have to sign NDAs. You can just clone. This is a fairly old process node. It's 130 nanometers, but it has a lot of nice features. It has the ability to have 5-volt I/O. It has a lot of extra functionality like MIM caps and Sonos shrunken cells, and a bunch of high voltage support by default. It's a very all-inclusive process technology. And as part of that, we were also able to take the documentation that's normally delivered as giant PDFs and publish it as searchable, readable, HTML documentation that just anybody can look at. Here's kind of a screenshot from an earlier version of it. And here's an example of the documentation. And we can include things like this stack up diagram, which if Matt can make that giant pop-up go away, maybe you can see the full details about. Well, that doesn't appear to be happening, so I'll just continue. If you look at the process technology, you can go and look at this stack up. It also includes a bunch of different standard cell libraries. And these standard cell libraries are actually quite comprehensive, and they cover a wide range of different types of use cases. You can see here a spreadsheet that I did to try and figure out, which cells are available in which libraries. We also, can publish, generated schematics and symbols, and we can even publish the GDS. And so today we have available, the digital standard cells, we have IO and periphery cells, we have primitives and DRC things, we have analog primitives. I know a lot of people have been waiting on this, but we have build space for SRAM available now. And hopefully in the next couple of weeks, we will also have a ReRAM PDK that enables you to use ReRAM on MPW4. This open source PDK data, I believe, is really important to filling out that fully open source ASIC result. And it appears that a lot of you agree with me, because in the first week after the PDK was released, the PDK got almost as many stars as traditional hardware projects like Yosus and Chijul, some of which have been around for 10 years. And if you look at the download stats, and these download stats are quite old now, but I haven't had a chance to update them, there are 200-ish new users on the PDK every week. If you told somebody in industry that they were going to get 200 new users every week on their PDK, they would tell you that there's no way that's going to happen. It's also seen a massive increase in the number of users, downloading tooling and being involved in tooling. We also have this massive community now that every time I give a talk, I have to update this slide because it's gotten bigger. There's 2,100 members on this Slack space that anybody can join, including you, and there's a big community there. This is just the start, though. The current PDK is a start. We need to continue to expand it. We're still trying to figure out how to deal with pull requests. There is, a whole bunch of pull requests there pending that I'd really love to get merged, but there are certain complications around that. And, the PDK data could use a lot of love. So we have partnered with NIST to do a recharacterization of the Sky 130 process technology, including characterization over wide temperature ranges. We're looking at, in 2022, having fully open source cloud-based TCAD for Sky 130. And I think this is super interesting because it expands the PDK's capabilities to areas that are traditionally underserved, like silicon photonics, quantum, and, we can even start exploring having things like carbon nanotubes and some of the other technologies Skywater has available. So I think the open source PDK release is going really well. What about part 2, the tooling integration? So for tooling integration, I had a focus on this groups of projects. And in terms of digital ASIC tooling, I strongly focused on the Open Road project. The Open Road project has its majority of its funding through the DARPA program, and I helped supplement some of that funding. As well, eFabless took what the Open Road project was doing and built Open Lane, which was strongly focused on Sky 130. DARPA really wanted Open Road to focus on GF12LP, which is a very advanced node that isn't open source. And so we were able to provide supplemental funding and work with eFabless to create Open Lane, which was very focused on the needs of Sky 130. As well, we worked with the OpenROAM project. And if you have been waiting, the SRAM bit cells have actually been live for a couple of months now. We just didn't really announce it. You can go and look at them. But the bit cells by themselves are not actually that useful. You have to combine them into arrays, and there are certain requirements around how you combine them into the arrays to make them manufacturable. And so Matt Goodhouse with OpenRAM has developed a memory compiler. He gave a talk about it at the FOSSI Dial-Up series, and that continues to improve and continues to iterate on that. And this is a fully open source project. You can go and help improve the OpenRAM project and help improve our SRAM capabilities. As well, one of the key things was how do we improve analog automation? And so I had two areas that I was looking at. One was FASOC from University of Michigan. When I started, FASOC was mainly focused on the proprietary tools. But thanks to some excellent work via MEDI, there's now an open FASOC which replaces all the proprietary tools with open source tools. And they have been successful in taping out designs in multiple MPWs. The first one, they focused on having design for an LDO and a mesh of temperature sensors. The second one, they went even further and started doing an analog mixed signal SoC, and used the OpenTitan RTL from Google's OpenTitan project to build a full mixed signal SoC using fully open source tools. They also have exciting things like continuous integration that includes automating checking of DRC and LVS errors on their repo. And I think this is a really exciting change for how we think about analog design. And, you know, the CI is now working for the temperature sensor and evolves a whole bunch of different work, but I think that's really cool. The other analog generator that we were looking at was the Berkeley analog generator from, Berkeley, or BAG as it's called. That has been less successful. At the moment, there are primitives available for use with BAG, but BAG still requires closed source software and Skywater's proprietary S8 PDK, which was the thing that existed before the open source PDK. Berkeley is actively working on producing a digital PLL generator and a SAR ADC generator using BAG, and the output of those will be usable on the open source PDK. But for now, you need access to these two pieces of technology. There's also many more. And if you think about the whole ecosystem, here is one attempt for me trying to draw a map of it. And what I'm really focused on is fully automated tools with open source PDKs and building out the IP ecosystem that covers that. And as I've been doing this, I've evolved my thinking a bit. As you can kind of see, my initial thinking was around tooling, IP, PDK. But the more and more I got involved in this, the more and more I started thinking about it from a software point of view, where you have the interface with the outside world that can come in digital and analog. You have the computation work, which is things like CPU and custom, digital logic. And then you have storage, which is things like memory and flash.
About fault injection attacks and how to defend against them.
I think there was a little bit of a mistake there. But as I was saying, you can think about this in terms of the needs of design. And so if you think about EDA tooling integration, you can start thinking about it in this diagram, where instead of thinking about them as separate things, you think about how do you use them. And so I think the Open EDA tooling integration is going really well. And lastly, the SiliconRealization Program. So we announced this open source shuttle program, and as Matt mentioned, it's a no cost to the developer. But what you do have to do is your design has to be fully open source down to the GDS. There are but roughly 40 slots per run, and you submit your design to eFabless, and it gets included in the MPW runs, and they handle all the manufacturing, distribution, all these type of things. To make that possible, though, there is a standardized harness, and the standardized harness allows us to get you back a large number of packaged I/O. Package parts. You get 10 millimeters squared that you can do whatever you want with, and the harness there enables you to have a lot more debug functionality, even though things like the I/O pins are much more limited and need to be configured in a certain way. So this has been evolving, and I expect it to continue to evolve and get more functionality. And so recently they added support for if you wanted to do analog design without them needing to do custom work. And one of the key things about this is we don't want your prototypes to be uniquely precious. Traditional MPW programs, you get back maybe 5 or 10 ICs that definitely normally raw die, which you then have to go and figure out how to package, which makes it very hard to share your results. It makes it very hard for you to group a lot of projects together. It also makes it super expensive to do lots of versions of stuff. And we really want people to try and fail, but then try again. And so how has the MPW program been going? Well, at the end of last year, we had MPW 1 go out. Middle of this year, we had MPW 2 close. And then there have been a couple more that are happening now. So MPW 1 finished, and there were 45 designs submitted for the 40 slots from 76 designers on MPW 1. And 60% of the designers on this were first-time designers who had never done a design before. And it covered a huge range of different types of designs. I was honestly surprised at how much variance there was in what people were doing. There was a lot of SOCs, that was expected, but there are also things like amateur satellite stuff, robotics apps, things like this. MPW has also closed out, and the thing about MPW 2 is 1/3 of people doing projects on MPW 2 self-identified as software developers like I do. And I think that's a really important change in, what this program is enabling people to do. Based on the Google program, eFabless also launched a commercial program. So if you don't want your design to be open source, or you have other requirements, like you don't want to be restricted to the style of packaging that the Google program has, you can go and put your design in the commercial program, and it's very cost effective. It's based on a lot of the learnings we've had from the OpenMPW program. We're also seeing some really awesome things, like Matt Venn, who's running this conference, developed this multi-project tools. And these project tools are compatible both with the Google MPW program and the eFabless Chip Ignite program. This means with the number of ICs we get back to people, that you can have 16 projects in one slot and everybody still gets 5 ICs. If you take the cost of doing a private MPW with the Chip Ignite program, that makes it less than $1,000, about $610 per project. And so if you look at our schedule, this is kind of what it looks like. And I want to be clear, it's not too late for 2021. There is MPW3, which I think has another week before it closes. Then there's MPW4, which will probably close at the end of December, if I understand correctly. And there will be more in 2022. But I highly suggest that you get your design in every MPW. You should be submitting your design every time you can. So as I said, the third run was supposed to end in October, but it's kind of pushed out a little bit. The one will go out, MPW4 will go out in December 2021. There'll probably be 4 runs in 2022. And the interesting thing is MPW4 will add the ability to use ReRAM. So if you ever wanted to try ReRAM in your designs, then MPW4 will give you that ability, and the PDK should be out in the next week or 2 that enables you to do that. So what are the plans for the future here? I think we've been quite successful. We're looking to add a second foundry and expand more programs that have a similar style, no-cost MPW program. And the one that's most likely to happen next year is a second foundry with a budget 180 nanometer process. I know 180 nanometer is an extremely popular process, and it's likely there'll be 3 runs of that next year as well. So not only will we have the 4 Skywater 130 runs, we will also have probably 3 180 runs next year. So there's going to be plenty of opportunities to do tape outs. As I mentioned, we're also trying to build up the capabilities for doing a lot more advanced stuff with things like TCAD. And we really think that this OpenPDK is enabling IP and tooling to advance significantly quicker than what it was previously. The delta in quality of the tools between MPW1 and MPW2 is absolutely massive. And we've seen a huge amount of really interesting things done by the community. And so this is kind of the call for help section. My team here at Google is only a small team, and we're trying to do a lot. And, we're not an ASIC design team. We're a software team trying to do new things in new ways that have never been done before. We're working with a lot of partner organizations, people like, the OpenTitan and Low Risk and FOSSI Foundation, the Open Compute Project, CHIPS Alliance, RISC-V, Open Power Foundation. We're also working with a huge number of academic partners. If you want to be a partner, key things is that you shouldn't be using proprietary tools or proprietary PDKs. And the most important aspect is creating an open source project. And for everybody on the stream, you can help. as I mentioned on MPW1, 60% of the submissions were from first-time designers. And I want to be really clear is it's okay to fail. Doing new things is hard. You will fail sometime, and you should try again. The reason we don't have just one MPW run is because we want to see people try stuff, learn from it, and improve. So this is a really important aspect, is that we are going to see people not create successful working chips, and that's okay. If you continue to learn and you continue to iterate until you get to a successful working chip, that is 100% working as intended. And so I do think I also want to mention is that there's been lots of surveys from groups like Siemens about surveying professional ASIC designers, and less than a third succeed 100% on their first design. And these are people who have been doing this forever with tools that are extremely expensive and extremely large teams. So it's expected that things are going to take a while to improve, and they're going to take multiple attempts to get right. It's going to take multiple attempts to get right. And that is the expectation here. I come from a software world. My software never works first time. It probably doesn't work, the 100th time I run it. And so this is perfectly fine. I would like to see a lot more iteration. So if you want to get notified, there's a mailing list you can join, and there's a Slack space. I do want to encourage everybody to come and join the Slack space because there is over 2,000 people there. It's also bridged to IRC if you have some type of objection to Slack, but only the main channel. And there's lots of activity going on there. There are groups focused around analog design. There are groups focused around developing new courses. There are groups focused around RISC-V. And so that's the end of my talk.